Hello students, and welcome to this lesson on inscribed angles and other intersections on a circle. Our objective today is that we will apply theorems about inscribed angles and intersected arcs using journal notes. So our first theorem has to do with the intercepted arc when we're looking at an inscribed angle. And remember, the inscribed angle is this angle here, A, B, C. So we can say that there's a relationship between the value of the inscribed angle and also the arc AC. And what we'll say is that if we've got 40 here, right, then the arc is actually going to be 80 degrees. And so our theorem can be stated as the measure of angle B, or the inscribed angle, is equal to 1/2 the arc AC. And in this case, we see that the measure of angle B was 40 degrees, and the arc AC was 80 degrees. And so this is a pretty obvious theorem. Our second theorem is going to be if two inscribed angles intercept the same arc, then those angles are congruent. So what does this look like? Well, if I've got two inscribed angles that intercept the same arc here, then we can say that these are congruent. In other words, I can say that if I have this, we can call this A, B, C, D. We can make a congruency statement such that angle A, C, B is congruent to angle A, D, C. This is actually supposed to be ADB. And so that's our congruency statement, which gets made here. So we're on to Theorem 3. And Theorem 3 is also a pretty simple statement. What Theorem 3 says is that if you have this angle here, and it's inscribed on a semicircle, so that means that this right here is a diameter, and you inscribe it so that the angle is on the ends of the diameter, then what we'll say is that this must be a right angle. And that makes sense because a semicircle on this side was 180 degrees, and so actually by Theorem 1 we can actually come up with this idea ourselves, but this is just a statement of it to make it a little bit simpler. Now Theorem 4 is a little bit more interesting. What Theorem 4 states is that if a quadrilateral or a four-sided figure is inscribed in a circle, then the opposite angles are supplementary. So in this case, right, every pair of angles that are across from each other will add up to 180. And intuitively this makes sense to us because I know that these two angles, right, if I were to talk about this arc here using these 2 points and this arc here on the other side, those two arcs would have to add up to 360. Well, what's half of 360? It's 180. Therefore, these interior angles end up being supplementary to one another. So those opposite pairs are supplementary. So in Theorem 5, we start to get into tangent lines and also chords. So Theorem 5 is going to be about when a tangent line and a chord intersect. So what this theorem will state is that the measure of angle C is going to be equal to 1/2 the measure of BDC, which is the arc. And in this case, so if we say that in green here our BDC is going to be 90, so BDC is 90 degrees, then what we can say is that the measure of angle C is going to be 45 degrees. So that's the relationship that we see there from Theorem 5. Theorem 6 is going to be about two lines which are intersecting inside of the circle, so two secant lines that intersect inside the circle. So this is where we get into relationships with multiple curves. So what we can say here is that given these three objects, so two arcs and an angle, what we can say is that if we have this large arc here, which is x, so x is the larger arc, And we can say that the measure of angle Z is going to be equal to 1/2 the measure of arc X plus the measure of arc Y. So in this case, let's go ahead and see what it would be. So I'm looking for the measure of angle Z, and I know that it is 1/2, and X is the larger arc, so that's going to be 85 plus 25. And then this is going to end up being the measure of angle Z is 55 degrees. All right, so now let's move on to Theorem 7. And Theorem 7 actually has a few different iterations of it, right? So it's all the same thing, but it's all for intersections outside of the circle. So for intersections that occur outside of the circle, right, where your intersection point is out here and not inside the interior, it's going to be a very similar formula to our previous theorem. And what we can say is that the measure of angle Z is going to be 1/2 X minus Y. And this is the key thing here, right, is this subtraction that's occurring in here. So you have X minus Y. And remember, your X, and this is why we kind of said it in the last one, was that your X is your larger angle, or arc rather. And that makes sense to us because we're still going to have a positive angle for Z, right? So it wouldn't make very much sense if we ended up with a negative number or if we used the larger number as Y here, right? Because we would end up with a negative. So these are going to be the hard ones, the outside of the circle and the inside of the circle. So just remember here, this is going to be a plus, right? So if you're inside of the circle, you're using a plus. Your intersection point there is inside the circle. And if you are outside of the circle, then you're going to be using a minus or a subtraction. All right, so your reflection today is, given the circle below, identify the name of the theorem that you would use to solve it. So start thinking about that. It might not match any of your scenarios directly, but you want to note where your intersection point is, right? All right, so have a great day, and if you have any questions, let me know. Make sure to get your reflection stamp and also to have a great day.